Okay, so starting off with our synthesis reactions and also with our question, looking at question number 1 as we're going to. Question number 1 is a metal oxide. That doesn't apply here. This is a basic one from last year. Synthesis reaction, you have a metal plus a non-metal giving you a binary salt. Binary meaning 2 elements, 5, 2. And so this one's just like kind of straightforward from last year. Binary salt. Not too hard. Okay. Everything in here has to be kept because looking at the phases now, as you see the phases now, solid, gas, liquid, solid, gas, solid. The only times you would take out spectators is if they're AQ on both sides. So none of these things are ever going to be spectators if they're solids, liquids, or gases, because they're pure substances. Okay? So really the only ones you need to look at for canceling and getting rid of spectators are when you have aqueous solutions. Okay? Now, metal oxide. So this is the first question, but also number 2 in your packet. Added to water, you're going to get bases. This is important. Okay? Barium oxide plus water is going to give you barium hydroxide. Now there's one little extra added tidbit here, because what you should see is the barium hydroxide falls in that class of the strong bases. And when it's strong, it breaks apart and completely dissociates. So when you do write out the net ionic equation here, you're supposed to be breaking it apart. So going from the regular equation down here to the net, you would have to do that final step of realizing it's a strong base and you dissociate it. Okay? So metal oxides obviously are metals with oxygen, and what is created when a metallic oxide reacts with water, you're going to get bases here. And then what is meant by a strong base? Basic just there. It needs to be dissociated and broken apart because that's what it does in solution. It completely ionizes, forms those ions. So these are kind of the terms: dissociated, completely ionizing, breaking apart, all those. All right, non-metallic oxide. You've got the non-metal with oxygen. Okay, that happens to be in our example here, carbon dioxide. Add it to water and you're going to get this carbonic acid. So you're going to get an acid out of it. Okay? And another special note here is that when you're looking at these, the oxidation number for the carbon needs to stay the same. Okay? And because you take your carbon dioxide, you're bubbling it through the water, you end up with an AQ, aqueous solution. So do pay attention to those phases. They are kind of important. And oh, by the way, this is a lot of information, and no, we do not expect you to have it memorized overnight. That's why I said, like, the questions here are supposed to guide you through what's really important that you need to notice about reactions. But do you have to have everything memorized? No. Okay, as we go through the units, we're going to embed the reactions along with it, but we want you to give you an overview so you know what you're looking for. And you can always keep your summer assignment packet with the reactions handy to refer back to when you're doing the reactions, okay? What is created in solution when so that we got is an acid. Now, what does it mean to be a strong acid or a weak acid? Here, this slide is showing you the weak acid part, because carbonic is a weak acid. Weak acids, as before we decided, only partially dissociate. So most of them stay together. Okay? So in that case, the weak acid is going to partially dissociate. So when you write the net ionic over here, it stays together. The only time you break it apart is if it's a strong electrolyte, like a strong acid, strong base, or a soluble salt. Those 3 cases is when, and you know it's going to completely dissociate, you break it apart. Okay? So that's the part of the question number 6. Now looking at the rest of 6 here. Question?
So number 3, what do you mean?
Strong base means it's going to completely dissociate. So you would break it apart. Anything strong electrolyte, soluble salt, strong acid, strong base, they completely dissociate. And remember, your strong bases are your alkali metal hydroxides and calcium, strontium, barium. So it's the heavy group 2 metals that are the strong bases. The acids are just the 7 you got to remember. The 7 strong. Okay? So let's look at what does it mean to be a strong acid. Here, this one I don't believe is in your packet. I threw this one in to show what the strong acid would look like. This one is the dichlorine heptoxide example where it's forming perchloric over here. Just showing you that because perchloric is a strong, over here in the net, you're going to see it broken apart. You're going to see it dissociated. So you would break apart the perchloric because the perchloric is one of the 7 strong. Okay? So strong acid break apart, weak acid keep together when you're writing the net ionic equation. Okay? So this one I threw in there as extra to help you see the difference there. Metal oxides with non-metallic oxides give you compounds with polyatomic ions. So in this case, this particular example, those polyatomic ions, we have calcium oxide, sulfur trioxide giving us calcium sulfate. I believe in your example it's sodium oxide plus sulfur dioxide giving you sodium sulfite. But still, same idea here. The only thing you have to watch for is depending on which one you're forming. We're going to get into the redox stuff in the part 3 notes. So if you don't get the charge thing and what I'm doing right now, it's okay. We're going to revisit how to do the charges and assign the oxidation numbers. But if you remember anything about oxidation numbers from last year, oxygen always has a -2. So this guy would be worth a -6 because there's 3 of them, right, in terms of their total charge. That means if there's only one sulfur, what's its charge going to be as it is in the compound? Its oxidation number should be a +6, right? Because those would have to add up to 0 since there's no charge on the SO3. When you're deciding which one it's going to be, is it SO4, sulfate, or SO3, sulfite, you would want to carry over the charge of the sulfur. So if you look here at both of these, this is also to help you answer number 8. Okay. This time the oxygen is still -2, so this brings in a -8 total because there's 4 of them, right? In this case, the charge needs to add up to a -2 though, because there is a charge on the entire compound. So in this case, the sulfur is still a +6. However, if you looked at sulfite here, you would still make this a -2, so this part would be -6. But we still would want it to add up to -2. In that case, the sulfur would have been a +4. So in this case, with our calcium oxide and our sulfur trioxide, we would want to go to sulfate, keeping the S's both at +6's. Now, if you had the sulfur dioxide, I believe that's when you would go, because that one, SO2, right? So that's a -4 over this side. In this case, the sulfurs are the +4s and the sulfur dioxides. So you would go to the sulfites. Once again, you're having trouble with redox and oxidation numbers. We're going to go through this in an entire note set next week. So just keep that in mind. You're looking to make sure that you're putting in the right polyatomic based on the right oxidation number. All right, metallic carbonates decompose into metallic oxides and carbon dioxide gas. So number 9, what gas is produced when carbonate decomposes? Carbonates always produce, in a decomposition reaction, CO2. And I did this one last year. I don't know if your teacher did. We did copper 2 carbonate, and we heated it up. The powder turned black, but then they had to light a wooden splint, stick it in the test tube, and the splint went out. I mean, the flame went out because CO2 extinguishes flames. So that would be an example of the decomposition. But we had to heat it up to get it going because it's an endothermic reaction. Once again, another concept we'll talk about later. But as you see, you get a production of a gas, and you're going to get a metallic oxide out of the other product there. And these are things that you're going to start recognizing the patterns on. Okay, this is going to break down CO2. What's left over? The metallic oxide's left over, because they're going to balance quite nicely. Now for the chlorates. Chlorates like to decompose into oxygen and metallic chlorides. Metallic chlorides and oxygen. So NaClO2 here for sodium chlorate. Okay, that's just the pattern that it follows. Now for the ammonium. Ammonium, this one actually is also incorporating our carbonate example too, because we have ammonium carbonate to begin with. But when the ammonium part decomposes, it's going to produce ammonia gas. Ammonia gas from that particular aspect. Now, if we're revisiting the other slide, the carbonate part is also going to decompose into your carbon dioxide. So, realize that as you're looking up here. Ammonia gas, ammonium to ammonia. I know it gets confusing because they sound very alike. NH4 plus goes to NH3. A couple other ones that aren't in the questions, but are probably in the packet, like hydrogen peroxide does naturally decompose and break down into water and oxygen. So series of one. That one's kind of a random one, but you know, known. This one is also another example of that ammonium compound breaking down into ammonia gas. In this case, it's ammonium hydroxide you're starting with. But you see that pattern, the ammonium breaking down into the ammonia. Now for some other ones that we definitely need to know in terms of decomposition. When we form our sulfurous or our carbonic acids, this is kind of the little trick here. They both automatically decompose. It starts like a secondary reaction. So if you form carbonic or you form sulfurous, it doesn't just stay as those compounds. It just spontaneously, rapidly decomposes into water and sulfur dioxide for sulfurous. Carbonic instantly goes to water and carbon dioxide. Now, I don't know if you're familiar with that one, and we're going to revisit this towards the end of the notes as well. The volcano reaction, people dump vinegar and baking soda in it. You've heard of that, right? Okay, well really that's acetic acid, weak acid, sodium bicarbonate. There's a carbonate there. So when you put the two together, it makes carbonic acid. And then the carbonic acid immediately decomposes, and that's where you get the bubbling, and it makes that nice bubbling effect. So if you've haven't ever mixed baking soda with vinegar, you can do it at home, but it's going to bubble out, and that stuff that's bubbling out is actually the CO2. Okay, so it doesn't stay carbonic for very long. It instantly starts the secondary reaction and decomposes immediately. So for both of those situations, if you ever see them forming as a product, you continue to decompose them and make them part of the net ionic equation. Like I said, we're going to revisit this concept towards the end of the PowerPoint too. All right. And this is the ammonium carbonate example, once again showing you decomposing ammonium to ammonia and carbonate to carbon dioxide. All right, on to decomposition, regular one. This is like your number 6 in your packet. The binary salt here, potassium nitride, is just going to break apart into its elements. Just as the standard decomposition one from last year. Okay, not in the questions or anything. They're easy to recognize, break apart. And you do realize that in this case, in order to get a ionic salt to be able to be in molten stage, it needs a lot of heat. So, because ionic salts have very, very, very high melting points, but this is kind of one you saw a lot last year when you were balancing equations and so forth. Question? No? Good?
I was going to ask, like, you said sodium bicarbonate and acetic acid produce that other thing.
Carbonic. Mm-hmm.
And that produces water and carbon dioxide, right?
Correct.
So at the end of your reaction, you should be left with water, correct?
Correct.
That would be drinkable, right?
Yes. Well, I mean...
Really?
Okay, so if you do just the quick little neutralization reaction, what you're going to get is sodium acetate. Now, remember, the acetates are always soluble. So this is just the molecular equation. Then you would get H2CO3. So this H basically, what does it do? It goes with that, forms the two there, and that recombines with the acetate, right? Well, these guys are just spectators, right? They don't react, they don't do anything. Okay? So really what we have here, if we were doing our net ionic, we'd have our H+, which is AQ, because this is reacting, plus our bicarbonate, this is AQ, and it's going to make our carbonic acid AQ. But this doesn't stay carbonic. It automatically decomposes into CO2 and H2O. So when you're writing your net ionic here, if you were to write your net ionic here, this is really what it would look like. You would skip that part completely. It would get kicked out of the equation.
So that's why you're doing that.
That's why the sulfurous and the carbonic are special circumstances, and ammonium hydroxide, there's 3 of them. There's special circumstances where they just immediately decompose.
So ammonium always becomes ammonium.
Well, ammonium hydroxide will decompose immediately. Just like, well, we're going to get back to these 3 at the end. Like I said, I'm going to hit them again. Just so you know and understand that when you see any of those 3 products form, know to automatically decompose them. Okay? Like I said, you're not going to know this overnight. You're not expected to know this overnight. We're giving you an overview, so as we go through all the units, we embed the reactions with the units. We'll hit them again individually with the units, but we want you to know what you're looking for. Have a good idea, and have your packet handy as you're going along and looking at this stuff. Okay? All right, for the activity series. I put this one in here just to show you, and there's one in the back of your textbook too, and you can Google them at all times. You're more familiar with this activity series, where it just lists the elements in terms of the most reactive up here to the least. The most reactive is lithium, gold is the least reactive, and do realize that hydrogen does some replacing and is in there as well. On the nonmetal side, fluorine is the most reactive, iodine is the least reactive, and it's usually just a halogen replacing a halogen here. But what you're going to see in your problem set is this activity series. It means the same thing. Guess who's still at the top? Lithium, who's still at the bottom? Gold. But it's also showing you the redox taking place here and the electron exchange. You don't need to worry about this so much, but what you should be recognizing is in any single replacement reaction, you do have a charge change going on, an oxidation number changing. So all single replacements are always redox. Actually, all reactions are going to have a charge change and electron change, except for double replacements. So keep that in mind. You might see this chart, but don't be freaked out because you see electrons in it. Still realize lithium's the most reactive. It's going to replace anything on the list. Whereas gold is the least reactive. It's not going to be able to kick out any of the other metals if they're in the compound. Okay? Just realize that really all of these reactions do involve some kind of oxidation number change, and that means electron change, and it means it's a redox. Everything but double replacements. So here, looking at single replacements, this is one of your basic ones, but do realize that we are still now breaking apart all of our soluble salts. So that iron 2 chloride here, iron 3 chloride here is going to break apart because it is a soluble salt. So you would break it apart. And the calcium chloride is also a soluble salt on the solubility rules. You would break it apart. And then your chlorides end up being spectators. So you would take them out. And your real single replacement reaction looks like this if you're in that ionic form. 3 calcium solid atoms plus 2 iron 3 ions give you 2 iron atoms and 3 calcium ions. The chlorides don't really do anything. So this is a single replacement, but changing it over into looking like a redox, because it actually is a redox. So this is that step up from honors and from regular chemistry. Now really looking at what's happening in the reaction. We're going to hit redox next week. Once again, if this seems out there, not to worry. Okay. Active halogens will replace less active halogens. So this case, this is one kind of from last year as well. Chlorine is more reactive than iodine, and since iodine's in the compound, chlorine can kick it out, take its place. And it does. And so we get some iodine crystals out of it. But once again, you're looking for the net ionic. In this case, the potassiums end up spectating. They don't participate at all in the reaction, so you would take them out.
Because they're soluble.
Because they stay soluble. Yes, they stay floating around in the water. They're not actually forming or breaking any bonds. Yep, new substance. And so what it looks like here is you've got your diatomic chlorine reacting with 2 iodide ions, giving you 2 chloride ions and some iodine solid crystals. Okay? And it's an exchange of electrons, 2 electrons going. All right, active metals. Now this one does answer question 13. Active metals will replace hydrogen in water, producing a base and hydrogen gas. Now, did everybody watch that video last year of the alkali metals, putting them in water, and it got more explosive every single time we went down the, boom. Like sodium gave it a little pop, but then you put potassium and you got a little bit more of a spark and flame. And then rubidium, I think, broke the, or was it cesium that actually broke the water container? But they're very reactive in water, and the reason why they're called alkali metals is because alkaline, it means basic. They form bases when they're put in water. And once again, sodium hydroxide is one of your strong bases. So over here in the net ionic, you would break it apart. Active metal, we get, what gas? We get hydrogen gas. Okay? So active metals replace hydrogen in acids to produce an ionic compound in hydrogen gas. So you see hydrogen gas is the other repeating thing here, H2. Hydrogen gas is highly flammable, and when you do light it, it makes a huge, loud popping noise. But in this case, they're going to get the lead to chloride, which ends up precipitating out because it's insoluble. It's one of those exceptions to the chloride rule. You would break apart your hydrochloric, because hydrochloric is a strong acid. So you're kind of going to start to see these patterns as we go along through the reactions. And in this case, nothing gets dropped because we get hydrogen gas, we get a solid out of it, so everything is needed. Nothing really spectates. A couple more. Lithium is placed in concentrated nitric. Once again, you're seeing that hydrogen is produced. This case, though, the lithium plus your nitric breaking apart here, you end up with the lithium ion, nitrate, and your hydrogen gas. So nitrate actually does spectate, and you would take it out for the net ionic. But you just break apart your things, and if they're the same ions on both sides, you can cross them out because they become spectators, and they're not actually participating in the bonds breaking, the bonds forming, in the new substance. Sodium is added to acetic acid, just another example of hydrogen gas being produced. And here, once again, recognizing that acetic, vinegar, weak acid, you have to keep it together. So over here, when you get acetate and your hydrogen gas out of it, nothing's spectating. So you can't cross anything out because the weak acid stays together over there. So just be careful with that. What stays together, what has to break apart, you know, note that as you're going along. The double replacements. Now this is number 15 on your questions. Formation of the precipitate, which we've been talking about in the last couple, set of notes. Formation of a gas, we've been talking about that today. That's kind of a double replacement. And then acid-base neutralization. We're also going to hit that next week. So these are the common types of double replacement reactions: formation of precipitate, formation of a gas, and acid-base neutralization. So looking at question 16, what do you consult when determining if an ionic compound will be solid or aqueous in water? What are you going to consult? Those solubility rules, definitely for number 16. You would consult your solubility rules. All right, so let's look at precipitation. We've kind of been through this the last set of notes. You have your two soluble salts over here. In this case, you have the one that precipitates out. Then you cross off your spectators, and you end up with your very small net ionic reaction. So we hit that in the last set of notes. That's pretty easy. Formation of a gas. These are the three, and like I said, we were going to re-hit them at the end here. When produced in a double replacement reaction, what three compounds will immediately decompose? These are the ones. So if you see in your double replacement, you end up with carbonic as a product, or sulfurous as a product, or ammonium hydroxide as a product. Those are any product of your reaction. They undergo that secondary reaction immediately. They do not, stick around. So you need to remember those three to automatically break them down into the water and the CO2 for carbonic, the sulfur dioxide for sulfurous, and the ammonia for ammonia. Those main three have that secondary reaction. And we showed examples previously in the slides where these things can be produced. All right, so here we go. One example, we have potassium carbonate, acetic acid. We get carbonic and we get potassium acetate. Now, note the carbonic is produced, so it breaks down into its carbon dioxide and water. And then you see your acetates are spectating and your potassiums are spectating. So you don't really need to include them, and you would end up writing the net ionic without them. So that's one example there. Here is an example where sulfurous gets produced. Magnesium sulfite hydrochloric gives you the sulfurous and magnesium chloride. Now you will notice too that this has to stay together because it's a solid. Solid liquids, gases always stay together. They never break apart. We do have our strong acid here though, so we want to break that apart. We're going to get the water and the sulfur dioxide from the sulfurous instantly decomposing. And then you're going to have your magnesium chloride. Now the magnesium has to stay in because it's part of the solid over here. So that's not a spectator, it's part of the solid. The only thing that does get crossed off is going to be your chlorides, because they do break apart and just float around in the water, and you would take those out. And last but not least, this one's showing you the ammonium example, where you get that ammonium hydroxide as your product. It's going to break down into the ammonium and the water, okay? And potassium hydroxide as one of the reactants is strong, so it'll break apart. This one will break apart. The ammonium compounds are always soluble in water. Remember, that's the group 1, or number 1 on the solubility rules. Ammonium is part of that rule. So that one would break apart. So you end up with the K's and the F's being spectators. So this would be really like K plus. The F's would just be F minuses, so they would cross off. So you'd have your ammonium plus your hydroxide giving you the ammonia and the water. All right, acid base. So this is number 18. Acids react with bases to produce salts and water. Now, 1 mole of the hydrogen ions will react with 1 mole of hydroxide, and that's where you get your 1 mole of water. And this is when strong acids and strong bases happen because they completely dissociate. So the weak ones will stay together. So number 18, what are you always going to have if you have a strong-strong? Strong-strong is always going to be H plus OH gives you water. Because the other ones will spectate. So say we had HCl plus NaOH. That's going to give us NaCl and water, right? So if I broke apart these into their ions, I'm just going to skip writing the AQ. Why are we not writing? What's the same? Cl's the same, Cl's the same. Sodium's the same, sodium's the same. So that's where you get your H plus your OH giving you water. So that always is going to happen if you have a strong combination. Strong acid with a strong base. Always just going to be that simple net ionic H plus OH minus gives you water. Now, in the case where you have weak ones, the weak ones have to stay together. So here we would recognize hydrofluoric as a weak one. It's the one halogen that's weak, right? Doesn't break apart. Lithium hydroxide, though, lithium's a group 1 metal, so that one's strong. So you break this one apart into the Li plus and the OH minus. Okay, we know that the H and OH are going to combine to form the water. And then over here, the lithium and the fluoride would be floating around. But because the fluoride is attached to the H over here, it cannot spectate. It doesn't go away. The only ones you would be able to cross off are the lithiums. And then you get your net ionic here. So keep the HF together. The only spectator ends up being lithium. And there you have it. So what is different about writing net ionics containing weaks? You got to keep that weak acid together, and you won't have as many spectators to cross out. One other thing to mention about acid-base neutralization, equal moles, okay, are mixed. But what you need to realize is that on the phosphoric has how many H's on it? 3. It's a triprotic acid, right? Triprotic. Remember that? And remember, each H is considered to be a proton because all H's is 1 proton, 1 electron. You take the electron off, it's H plus, it's now just a proton, right? So that's why we say triprotic. All right, so if you have a mole of sodium hydroxide, you only have 1 hydroxide for every time the sodium hydroxide breaks apart. So it only has the ability to neutralize one of the H's on the phosphoric here. So when you look over here, how many H's should still be attached? If it's 1-to-1 mole, that means that the OH can only take off 1 H when it's equal mole like that. So when you're writing out your product over here, you end up with dihydrogen phosphate. Now say you had 2 moles of this to 1 mole of your phosphoric. Then we could take off how many H's each time? 2 H's would come off, and then you'd end up with hydrogen phosphate. Okay? And if you had 3 moles of the hydroxide to every 1 mole, you could take off all of the H's and end up with phosphate. Does everybody see what I'm saying here? Because 1 H plus 1 OH is going to give you 1 water. But you got to have, in this case, you would have to have a lot more hydroxide because you have a lot more H's attached there in your phosphoric acid. Yes?
In that case, would be the case with combustion of water.
Yes, yes, you would rebalance it, of course. It would be rebalanced, but it's very mole dependent. You know, you got to look for that mole of H versus the mole of OH because they are 1-to-1. Now, your triprotic acids are your phosphoric and phosphorus. There are a couple diprotic ones, like sulfuric and sulfurous. I'm trying to think of some other ones, like I think oxalic is one. The carbonic really wouldn't count because it automatically decomposes, right? So, all right. But you're looking for the, mole relationship on the ones that have more H's when it's not 1-to-1, realizing that you're going to need more hydroxide in that case. Yes?
4 next to the
Yes, for here, this one?
Yeah.
That would be a 4, yes. So this is, every time you pull off an H, you end up adding 1 to your charge. So this is dihydrogen phosphate, and that would just be hydrogen phosphate. Combustion. Complete combustion versus incomplete combustion. But before we get there, what are always our reactants in a combustion reaction? Reactants.
Oxygen.
Oxygen's always one of them. And some kind of hydrocarbon. So it could be like a CH compound, like that. Or it could even be like a CHO compound. Or it could be CHON compound. But it's got to have those hydrocarbons in it, right? So you can have some oxygen, nitrogen, maybe even a little bit of sulfur sometimes. But you need that hydrocarbon, you need the C and the H's in there. But, so we're primarily looking more like at these types here. So those are going to be your reactants. What kind of products do you get if you get complete combustion? Straight up carbon dioxide and water, just like last year, normal. These are complete combustions. But what if there's not enough oxygen present? We get the incomplete products, and that, so you get that nasty what? CO, carbon monoxide. Does everybody know that carbon monoxide is very, very bad for us?
Yeah, there's whole sensors that you put in your house.
Actually, I have, yes, and realize that it needs to be towards the floor because the carbon monoxide actually sinks. And yeah, I have one in my basement as well, of my 3-story townhouse, because it's really nasty stuff, and you can't smell it, you can't tell it's there, you need a detector. Basically what happens, problem with carbon monoxide, is that it outcompetes oxygen in binding to our red blood cells, with the iron in the red blood cells. So it's kind of like it suffocates you from the inside out. And you turn like bright red and
There's a
be
story
very
about a
dangerous.
lady who noticed her cat was acting weird, and it was like the middle of the night, so she called the vet, and then the vet noticed her words were slurred, and she's like, "Get out of the house!
Get out of the house, there's
Carbon monoxide."
Wait, hold on a second, question? Yes? You run out of oxygen. Like there isn't enough oxygen in the reactant to completely make all of the carbon dioxide, so instead you get some CO out of it.